And large loop antennas, here's my forte. Loops of wire that completely enclose an area, normally one wavelength or greater in circumference. Can be circle, square, or triangle. A circle is actually the most efficient, but it's hard to build. Major lobe is perpendicular to the plane of the loop, and a null is in the plane of the loop. Multiple wavelength loops, many lobes and nulls. They're talking about a single loop now that's used on multiple bands. We'll have quite a few lobes and nulls, especially at the higher resonances.
Hey Steve, I got a question. What, will that antenna mess with my bees?
Which antenna?
The Yagi
Mess with you?
honeybees
No, it shouldn't at all.
at all?
No?
Okay.
No, then that would be entirely dependent on frequency, and you'd have to know what frequency they were
The bees
sensitive
are
to.
on?
Yeah.
What their resonant
So,
frequency
for
is.
instance, our bodies, a 6-foot person is approximately resonant at 2 meters. That's the body's resonance. A bee, where's he going to be resonant?
She.
Microwave.
Okay, somewhere on microwave frequency. So where we are on most amateur bands, no, that's not going to fit the bees.
Okay. Good.
Multiple wavelength loops, many lobes and nulls, combined vertical and horizontal polarization pattern. Why? Why would you have a combined horizontal and vertical?
The lobes going in different directions.
No. I'm not exactly sure why they have had that in there. I question that. Creates an essentially omnidirectional pattern with a peak angle of radiation somewhat lower than a dipole at the same height. We're talking about, like, say you took a wire and went all the way around the perimeter of the inside of this room. That's a loop. And you could put that through a tuner, and you break the loop at some point and bring it down with coax to a tuner. You could tune that up and it would work fairly well. But if it's lower down, most of the signal's going straight up anyway. It's an NVIS antenna. But it has a fairly broad bandwidth that the frequency you've cut it for, because it's one wavelength instead of a half wavelength. Small loop antennas, less than a third of a wavelength in circumference, the pattern reverses. Now the major radiation lobe is in the plane of the loop. You've got a loop here, and the radiation will be along that plane. Small loops have sharp nulls broadside to the plane of the loop. I have a little loop that goes on my 2 meter. You can get them on eBay. Look for 2 meter loop antenna. It's pretty cool. It cost me about, I don't know, 24 bucks. And it's just a little loop like that. But it makes the handiest thing for directional finding. You don't have any big antenna like this, and it's not going to be as sensitive, but it works fine, and it gives you a really good null broadside to the loop. So, a halo loop, that's a whole different deal. A halo loop is basically a half-wave dipole that they've pulled the ends around and they don't quite meet. So now you've got this half wave that's only the size of a quarter wave, and it's horizontally polarized. So they use these on 6 meters a lot because they can put them mobile and still have a horizontally polarized 6 meter antenna. It radiates most strongly in the plane of the loop, and when horizontally oriented, they're omnidirectional in the plane of the halo.
What's considered the plane of the loop? I'm
If
not.
it's like this, the plane of the loop
Okay.
is that way.
If this were continuous all the way around, this would make a loop antenna. If the whole thing was connected. Actually, that's the plane of the loop. This is also the plane of the loop.
So the
This is perpendicular to the plane of the loop from me to you. So if it's a full wave antenna, this is the broadside way the antenna propagates. You would
Off the
steer it like
sides.
this. The radiation would go out broadside to that full wave loop. If it's less than a third of a wave, it's too short. It won't propagate this way. it propagates that way.
Yeah, small loop antennas are used a lot for digital, and they can be as small as, you know, sitting in this room basically, but typically run with low power.
Yeah, the problem is the capacitor in them,
Yeah.
the tuning capacitor. Tuning capacitor has to get bigger and bigger to handle bigger power.
Yeah, but they'd be more efficient, would they?
So that's called a magnetic loop. when
Yeah,
that's
if you're,
small.
if you're dropping the, yeah.
The efficiency can be pretty good on a magnetic loop, but the size it is small, and the bandwidth is really short, or really narrow. So it means you have to constantly keep tuning it. Now they're developing automatic tuners that go with those magnetic loops. So you just tune to the space you want, it sets the tuner in.
But the expensive, really good ones have a vacuum capacitor that's
Yeah,
quite
yeah.
expensive.
Yeah, there's several $100 just for the vacuum capacitor.
Ooh.
Okay, so a quad loop, square loop with each side at 1/4 wavelength, and a delta loop will be each side at 1/3 wavelength. And loop arrays, cubical quad antenna. So it's like a Yagi, only you're using 1 wavelength loops. This monster, 1, 2, 3, 4, 5, 6 elements, that might work on 2 meters. And I have seen 2-element designs on eBay for a quad loop beam. And what's the advantage? Broader bandwidth.
A lot of gain.
So you have a lot of gain and broad bandwidth. You get them both. No free lunch with antennas. When you increase the number of elements, you decrease the bandwidth. So, okay, you create an antenna for 2 meters, and you make it a 7-element or an 8-element beam. The bandwidth is not going to go across the entire band. You're going to work one end of the band or the other end of the band. You'll work the FM band, part of it, for repeaters, or you'll work the single sideband end of it, but you're not going to get both. You go with a quad, you can do both. So, and there's different designs out there that are more broadbanded than others, but the quad is a simple way to get your cake and eat it too. So, cubical quad antenna versus a Yagi. The quad is more mechanically complex, yes. The reflector element is 5% longer, just like in a Yagi. The crossed arms are required to hold the wire. The quad has more surface area, higher wind loading, more susceptible to ice damage. I can verify that. And approximately how long is each side of the driven element of a quad? 1/4 wavelength. So they didn't talk about the positive aspects of the quad. Yeah, it is more mechanically complex, higher wind loading, higher ice loading, but it's quieter. You can hear DX that you can't hear with a standard Yagi. It has a little bit more gain. A single quad element has about 2 dB more gain than the same dipole. So you do have a little bit more gain, and it's a quieter antenna.
And your neighbors will think you're trying to communicate with them.
I had no problem with my neighbors. In fact, I told them there were advantages of this antenna because it wasn't as likely to get struck by lightning. And that is true. If you've got a wire that goes all the way around, you have no points. There's no end points. There's no bleed off to create a path for the lightning to come down and strike. My tower got hit anyway. So how does the forward gain of a 2-element quad compare to the forward gain of a 3-element Yagi? About the same. Yeah.
Gotta find the button
Yep. Well, what configuration of the loops of a 2-element quad must be used for an antenna to operate as a beam, assuming one of the elements is used as a reflector? There's a 2-element quad now. You've got 2 loops. One of them is being used as a reflector. And a reflector is going to be longer. The reflector element must be approximately 5% longer. That should be it, delta. In which direction is the maximum radiation from portable VHF, UHF halo antenna? Omnidirectional in the plane of the halo. So if this is my halo, and it's horizontally polarized, it's going to be in that plane, omnidirectional, all the way around.
That's on the wrong side of the block, it's going outside.
In which direction or directions does an electrically small loop, we're talking about a magnetic loop, have nulls in its radiation pattern?
Delta. Beats me.
There is a null, it's broadside to the loop. Yeah.
Oh, see, I don't get rest.
Now, there are caveats to that. I mean, this is not absolute. When you've got a loop, it isn't as affected as much when it's that close to the ground. But being close to the ground, it's still going to have that ground as a reflector, and it's going to change that broadside effect. So, yeah, you'll have a null that's broadside, and most of the radiation will go out in the plane of the loop. But because it's so close to the ground, a lot of that radiation is going up too. So you have this big squashed balloon that looks like that. It's more omnidirectional than it is patterned. It's not a beam. But that has to do with how close it is to the ground. If you put it, 20 feet up in the air, you'd have more of a beam pattern. So what's the combined vertical and horizontal polarization pattern of a multi-wavelength horizontal loop antenna? Okay, now we're talking a big horizontal loop, what's the combined vertical and horizontal polarization? Virtually omnidirectional with a lower peak vertical radiation angle than a dipole.
That's when you just gotta memorize.
Yeah, so this is the advantage that some people like to tout for a low band loop antenna. That it's omnidirectional, so it works like a vertical, but you don't have as much ground losses with it, and it has a lower peak vertical radiation, so it doesn't have as much radiation going up, more of it's down towards the horizon. So it might be a little bit better for DX. It's especially good if you're on 80 meters or 40 meters and you're trying to work stations about 300 to 500 miles away. One to two states. At least that's what it's touted. In reality, I don't really notice a lot of difference. Which of the following types of antennas offer the greatest gain? Hayagi. Specialized antennas. NVIS means near vertical incidence skywave, and we use that for short hop within 300 to 400 miles. Below a half wavelength above ground, a dipole is nearly omnidirectional with maximum radiation straight up. And that goes for any antenna except a vertical. Any half wavelength dipole low to the ground, most of the radiation is going straight up. Typically mounted 1/10 to a quarter wavelength above ground. That is your NVIS definition, and I'm sure that's on the test. So, at 80 meters, how high would a quarter wavelength be? How many meters? If 80 meters is a full wavelength, what's a quarter wavelength? 20 meters. Okay. How high is 20 meters? A meter is a little more than 3 feet.
Pretty high.
We're talking over 60 feet. Okay. So anything under 60 feet would be considered NVIS on 80 meters. I don't know many people that have their wire antenna up at 60 feet or above. That's pretty high. So they're all NVIS antennas. Now you get down to 40 meters and it'll be half of that. Now we're talking about 30 feet. And you get down to 20 meters, it's even lower than that, 15 feet. And there's a local install of a very, very NVIS antenna. These are only about 8 feet tall. So if you really have your antenna low, less than 1/10 of a wavelength, what are the detrimental problems? Well, one is ground losses. If you're 1/10 of a wavelength from the ground, a lot of your energy is going to get absorbed in the ground. That's not an efficient antenna. So the trade-off is to find a height, and maybe it's all dependent on how high your trees are, how high the edge of your house is. The trade-off is ground losses versus NVIS efficiency. Some people will get it up to about 1/8 of a wavelength, and they'll stretch out a wire on the ground directly underneath their wire antenna and make a reflector. They'll make it 5% longer, and now you've got a gain antenna that's going up, and that's actually quite effective. So yeah, it has a high angle of radiation. It's useful communicating with 300, 400 miles. Popular at 80 and 40 meters. And it's popular at 80 and 40 meters because most people can't mount any higher. Stacked antennas, you can mount 2 more Yankees side by side or one above the other. So there's 4 phased antennas. We've got 2, 4, 6 elements on each one. By phasing them this way, he's getting 3 dB more gain this way, and adding 3 dB more gain again in this. So he's really doubling it twice. He's really doubling it twice.
Also wind loading.
And doing the same thing this. So on HF, you'll see some guys with several stacked antennas that they can switch phasing between because they want to be able to direct how low an angle they get on the horizon. If they just use the single antenna at the top, they're getting one angle on the horizon. They could disconnect that and just use the lower antenna and get a higher angle for closer in stations, or they could phase them both together and really squeeze it to the horizon and work the DX. So you'll see antennas stacked like that, and they're actually being able to switch that phasing harness. Right, the distance between these antennas is not as critical. It can be a half wave to 1 wave. It's more critical what the length of the phasing harness is. Each piece of coax has its own electrical length as well as physical length, and you need to know what the electrical length is for the phasing. Log periodics, another of my favorite. I tried building one of these once and failed. I was doing a wire log periodic for HF. And it was much too complex. It was over my head. But what they're doing is connecting the odd pieces so that all of these are connected. And sometimes they use a double boom to do that. So what are the advantages? The length and spacing of elements increases logarithmically. Extremely wide bandwidth, up to 10 to 1. Widely used for TV antennas, so you can cover all the bands. It does have less gain than the Yankee. There's some controversy about that. You have a lot more aluminum up there in the air. They call that capture area. So you're actually providing more capture for the signal that's out there. It has less front to back ratio. So there's an amalgam or a hybrid between a log periodic and a Yankee called the log YAG antenna. And it'll often have a parasitic reflector and a couple of parasitic directors, and then a center section that's log periodic. Now you have wide bandwidth and a little bit more gain and better front to back. And they work like gangbusters. It's a lot of aluminum to put up in the air. They're expensive.
You got to build one of these.
A beverage. So is soldered together beverage cans to make a vertical.
Bruce did that.
Yeah. So a real beverage antenna is named after the guy named Beveridge who designed it. And it's a very low wire, maybe only 4 feet off the ground. Put it on fence posts. And it'll go for a wavelength or more, often 2 to 3 wavelengths. It's used mainly as a receiving antenna because it's very low noise and it's very directive. This lobe here is a huge directive lobe, very low to the horizon. They would often combine this receiving antenna with a big beam antenna and be able to hear Southeast Asia or India or, some really difficult stuff out there. It is a traveling wave antenna. What they mean by that is it's non-resonant and it uses a resistive load at one end. Yeah, full wavelength or more. Beverage is a single wire. If you go a double wire and go all the way out and you terminate that, you've got a rhombic. Rhombics have been used in the military for years. Put them on, 30-foot telephone poles, and oh my God, that's an antenna. That is an antenna. But you can't rotate it, but they'll have an antenna farm with maybe 8 of these spread out in different directions and just switch between them to get the beam effect.
There's a guy over at Chillicothe that has one of those pointed towards Mount Shasta, and he bounces that signal off of Mount Shasta and gets all over the world.
But yeah, they're interesting antennas. There's some big downsides with them too, but I'll talk about that. So the beverage antenna is inefficient, high losses, low gain, mainly for receive, but it's great at rejecting noise, greatly improves the receive performance on low bands. So like on 160 meters, that's the noise band. You talk about noise, you hear every thunderstorm for 1,000 miles, but this beverage antenna rejects a lot of that. So multi-band antennas. Few radio operators can put up a separate antenna for each band. Dipoles work well on odd harmonics. Random wire is a multi-band by definition, and multi-band usually refers to an antenna that configures itself for 2 or more bands. Again, there's no free lunch. A multi-band antenna is a compromise. It's not going to work as well as a single band antenna. So a single wire, resonant for that frequency, that's your ticket. That's going to be the most efficient thing you can put up. A Yankee is just a variation of that. You're taking a resonant driven element and putting directors in front of it and a reflector behind it. But you go a multi-band and put a bunch of traps in it. You've got capacitive and inductive trap. All you're doing is creating more inefficiency in that antenna. Multi-band antennas use traps. A trap is a combination of a coil and a capacitor. At resonance, a parallel LC circuit looks like an open circuit. So it's like it's not there. It can be used as an RF switch. It permits multi-band operation. So this is what I was talking about a moment ago. You've got a dipole antenna with traps for 15 and 20 meters. So the entire antenna works on 40, and then it also works on 20 and 15, because at 20 meters, it's not permitting anything to get past that. And it only sees this part of the antenna. At 15 meters, it won't permit anything to get past that. It's trapping the signal. And it only uses this part of the antenna. Specialized antennas. So a trapped dipole, wire between each pair of traps is a half wavelength dipole. The outer dipoles are shortened because inductors and traps act like loading coils below the trap resonant frequency. So we put up an 80-40 trapped dipole up on Providence Hospital so that Providence could reach their home base up in Portland if everything else went down. It works fine. When propagation's decent, we get a good signal between Portland and down here. We're using a trapped dipole. It's not the best, but it does work. And, sometimes you just compromise.
Yeah, it depends on the size of the lot you got, what trees you got.
I'm using a trapped dipole on 80 and 40 for my lot because I can't fit anything else on there. So, yeah, you use what you can use. Tri-band beam, 3 or 4 element Yankee with traps in each element. So a tri-band beam will have a reflector and a director, and then the driven element will have traps in it. In fact, they'll all have traps in it because they all have to be resonant. What's the near vertical incidence skywave propagation?
Bravo.
The short distance, right, MF or HF propagation using high elevation angles. Which of the following antenna types will be the most effective as near vertical incidence skywave for short skip communication and 40 during the day. You know it's not going to be a vertical.
Alpha.
A horizontal dipole placed between 1/10 and 1/4 wavelength above ground. The others are too high. What is the primary function of an antenna trap?
Alpha.
To permit multiband operation. What's an advantage of vertical stacking of horizontally polarized Yeagis?
Delta.
Okay, so be careful. The advantage of vertically stacking of horizontally polarized Yeagis, it's going to squeeze it closer to the horizon. It's not going to narrow down the horizontal beam part of it. It's going to narrow the vertical part of it. So yes, narrows the main lobe. Which of the following is advantage of a log periodic?
Alpha.
Wide bandwidth. That's it. So why would you want a log periodic? I mean, it doesn't have higher gain. Well, the military needed them because they were spanning a lot of frequencies very quickly. They used something called ALE, automatic link establishment. It's where your distant station that you want to contact and yours go back and forth automatically, like every 2 seconds, looking for a path. When it finds a path, they lock onto each other, and you don't know when they're locking on. The station operator, he sees a display, but he's not in control of it. It's totally automatic. It'll lock on, and the antenna takes care of that. The antenna doesn't care where it is. It'll span that entire frequency span. So they don't have to use a tuner. They don't have to play with automatic tuners. They're using an antenna that will take care of that whole thing. So which of the following describes a log periodic antenna?
Alpha.
The element length and spacing vary logarithmically along the boom. What is the primary use of the beverage antenna? For getting rid of your old beer cans. No. Directional receiving for medium frequency and low frequency bands. Which of the following is a disadvantage of multiband antennas?
Delta.
They do. They have poor harmonic rejection.